Think of any product that you use on a regular basis. Your phone, a camera, computer, your car, and try to imagine how that product got to you. Where did all the material come from? What was done to it? Who did it? Where? How did they ship it? How did it get assembled and tested and finally get to you? If you try to think of all the things that have to happen for you to get a modern product, what you imagine is this web of activities and people and machinery and transportation that spans the globe. It's a very complex socio-technical system. So what we would like is for those systems to run fast, to be cheap, and to be good. And so what my research does is it tries to answer questions like, how do we design these systems, whether we're talking about warehouses or factories or global supply chains? How do we design them? How do we manage them? How do we control them? And importantly, how do we tell if they're doing what we want them to do? That's what my research does, and the tools that we use are computing and mathematics. For instance, we're working on a project right now with a major avionics manufacturer. When they bring a new product into the factory, they have to be sure that they have enough resources in the factory to meet the commitments they've made to the customer. And the only way for them to tell whether they have enough resources for this particular project is to develop a simulation model. It takes time and it costs money to develop those simulation models. So what my team has done is we've developed a specialized way for people in the factory to be able to describe their own problem in their own words, creating a computational model. And then what we do is we automate the translation of their model of their factory into a simulation model. We're using some advanced techniques and methods from computer science. The result of this is an order of magnitude reduction in the time and the cost that it takes for them to create a simulation model, which means they can create more simulation models, they can look at more situations, they can consider more factors, and make better decisions about how to produce this particular product. They'll be more reliable to their customers, and they'll reduce their cycle times and their lead times. When I was a kid, I always wanted to know how things worked. So growing up on a farm, I was always interested in how all that equipment worked. When I went away to college, I discovered industrial engineering, and that's all about people and technology in large systems. And so I fell in love with industrial engineering. I was very fortunate to get my degree and come out at a time when computing was really coming into its own. And so over the course of my career, the things that I'm interested in, the problems I'm interested in, and the means of solving those problems, computing and mathematics, have been continuously improving, getting better every year. So that's what inspired me to begin with. What inspires me today is the fact that the problems are getting bigger and harder, so there are plenty of things to work on, but also the tools that we use are getting better and better, the computing and the mathematics. And the third thing is I'm surrounded by brilliant colleagues and students, and all I have to do is ask them the right questions and they'll figure out the answers.